Welcome to the lecture on computational optimization. This is an elective course in chemical engineering, but then we welcome students from other departments to come this course as well, since it covers general optimization problem. All the lectures will be recorded and will be posted on a course website afterwards. So here's the basic information of this class. You are already in this classroom. It's Tuesday, Thursday, 4:30 to 5:45. And occasionally we will have some makeup lectures because I need to travel from time to time, but it won't be too many times. I know some of you may have a class at the same time on Monday and Wednesday, but all the lectures will be recorded and posted on YouTube. You can watch the recording afterwards. So the makeup lectures are optional to attend, but you are required to attend the lectures if it's on Tuesday and Thursday because you did especially if you register for this class. And we will have an office hour on Wednesday, 5 p.m. to 6 p.m. in my office in Forney Hall. You are all welcome to stop by in the office hour. So what will we cover in this class? We have a course website. You can take a look. So this is the course website. And then from this course website, you can find the previous offering of this class in spring 2024. So what's the difference between this class and some of the other optimization class offered at Purdue? Actually, last time I offered this class, and then at the end of the semester, we got feedback from different students, and different students gave very different feedback. Some students say, this is too much mathematics content for them. Maybe some of the, especially chemical engineering students, are not so fluent in math. Then they think it's too much. And then there are other students who say, this is not deep enough. They are interested in a particular topic like nonlinear programming, and I only spend maybe 3 or 4 lectures on nonlinear programming. So how do you decide if this class is right for you or not? And how do you see yourself after taking this class? Let's start with the first type of people who have never studied optimization before, or who you feel like the math is not so strong, right? So I would say for the first type of people, the expectation would be after this class, you can roughly get 20% of what I covered in this class. Actually, that's what happened when I was a student in grad school. When I went to take some of the more theoretical class, I got maybe 20% at most after the whole semester. But then we will not fail you because you only get 20%. You will generally get pretty good grades, right? The goal here is not to fail you. So for all those classes I took in grad school where I only got 20%, I usually get an A+ afterwards. That's usually how it works in grad school, right? So afterwards, if you encounter similar problem in your research, you could read more about a specific topic, right? So this is just to give you overview of different topics in optimization, including maybe you can find in the course description. We cover different topics like linear programming, mixed integer, linear and nonlinear programming, conic programming, global optimization of non-convex problem, and decomposition algorithms for mixed integer programs. So for each of the topics, we spend around 4 or 5 lectures, right? We are not going the whole semester on a specific topic. So for example, if you think you are most interested in linear programming, Professor Andrew Liu from industrial engineering offers a whole semester class on linear programming, right? So maybe after you take this class and you think you want to know more about linear programming, you can take Professor Liu's class. And similarly, for other topics, there is a nonlinear programming class offered in industrial engineering as well. Okay, but what's unique about this class is that I think this is the only class that covers mixed integer programming, mixed integer nonlinear programming, and also global optimization for non-convex problem at Purdue. there are reasons for that. One of the reasons is that most of the optimization class usually offered in industrial engineering department, and for some reason the industrial engineering department decided not to hire someone working on integer programming. There are reasons for that. So if you are especially interested in integer programming and maybe decomposition algorithms for those problems, this will be the only class at Purdue that talk about those topics. Okay, and then we will also talk about some software packages to solve these problems. I will tell you more about that in the next few lectures. So roughly, the lectures will be 30% proofs, 50% algorithms and computation, and 20% modeling and applications. The reason we decided to do that way is because for modeling and application, typically once you learn a few applications, you can read the papers in your domain, right? And then you should be able to understand those papers. And the other reason we only did 30% proofs is that I'm facing engineering audience instead of math audience. Therefore, I will do maybe at most one or two proofs in each lecture. And the rest, the focus is on computation and algorithm. We will ask you to maybe implement some of the algorithm in the homework problems. Okay, so that's just a rough overview. And then if you are curious about what we offer, there are slides, YouTube videos, and homework problem for what we offered last year. Okay, so this is just a rough overview to decide if this class is right for you. And all the homework and videos will be posted on the website. We will only use Brightspace for making announcement and use that as a gradebook. The prerequisites for this class are calculus, linear algebra, and know some programming in Python. So maybe a very quick show of hands. Since we don't have many people here, we can make this class very tailored for you guys in the audience. How many people haven't studied calculus and linear algebra before? I assume if you are engineering or you must have taken a class. Yeah, how many people haven't programmed in Python before? Yeah, one. But yeah, it should be pretty easy now, especially with ChatGPT. It's much better than me in programming in Python. You should be able to learn. Do we have any undergrad in here? You are okay, welcome. So last year we have 2 or 3 undergrad. Actually, they made it to the top of the class at the end. Okay, hopefully that makes it more encouraging. And then the other thing, if you have never done some math before, probably this will teach you a more formal mathematical way of thinking. Okay. Yeah. Next Monday, we will do a recitation on calculus and linear algebra, because last year what I found is that my first lecture is very, very easy, straightforward to follow. Then starting from the second lecture, I find students started to get lost. The reason is because after you have taken linear algebra and calculus for many years, many people have forgot what they've done before. So we will revisit some of the basic facts in calculus and linear algebra just to get people warm up in next Monday. Okay.
So you said Monday,
yeah.
It would be during makeup time lecture?
Yeah, during makeup lecture the same time. If you have a conflict, no worries about that. It's not required for the, and then we will have the lectures recorded. Yeah.
Will that be here?
No, it will be from the previous slide, a different location. BHEE 236. I will, if you are not on Brightspace, I will add you to Brightspace, and then all the announcement will be made on Brightspace. Okay, yeah. Any other questions? Yes.
Those makeup lectures, they're at the same time, so they're still at.
Yeah, they are still. Same time. Yeah. How many people cannot make it on Monday the same time? 2 of them. Okay, yeah. So if you cannot make it, we will have the video posted And then you can ask questions during the office hour as well, or schedule a separate appointment with me. I used to do a couple makeup lectures on Zoom, and I find it's not very effective. People started losing attention, and there were no questions. The other thing I want to emphasize is that I would always encourage you to ask questions, because probably that's the main point for you to come to the lecture. As I said, all the previous lectures are already recorded and posted on YouTube. If you don't feel like asking questions, you could just watch those videos, right? You don't have to come to this class. And then from last year, I actually learned a lot from students' questions. They asked me many questions I didn't know how to answer in the classroom. Then I went out and read more papers and came back to them afterwards. So I would really encourage people to ask any tough questions you wish. It also helped me to learn. Okay. Yeah, so this is the evaluation. We will have 10 homeworks. Each homework will have 5 problems. The homework will be 10% of the total grade. Then the midterm and final will each be 40%. We will have a course project roughly 10%. Okay. And you can also get some bonus point. The course evaluation will be 1%. The other significant chunk of the bonus points are if you can find a mistake in the homework solution we posted. We have already posted most of the homework solution the homework we offered last year. It will be the same homework this year. Okay. But then the student who took the class last year made the solution. I didn't check carefully each question whether they did it right or not. So if you find a significant mistake in the homework solution, then you get a 2% bonus point, and then you can get up to 10%. Okay. Yeah, and then last year I received quite some complaints that this workload is too high for an elective course. Probably that is true, but then you can pick 60% of the problem in each homework if your research is not in optimization. So out of the 5 questions, maybe you can pick 3 questions. Or you could pick maybe 50% of each question, and for one problem, you solve the full problem, right? But then you are strongly encouraged to do the homework, and also strongly encouraged to do the homework by yourself before you check the solutions. You can never learn math or coding very well without doing any exercise. And then we won't grade the homework based on correctness. We will only check if you make a serious attempt or not. Okay, by a serious attempt, I want to clarify submitting a blank sheet is not a serious attempt. Last year, I got not only one student, but multiple students, each time they submitted a blank sheet and say they made an attempt to this homework and asking for the full grade. I hope this is clear enough. That doesn't really count. Okay. Yeah, any questions regarding the evaluation here? Okay. Yeah, so the lecture will not be based on any textbook. We will cover some content in the following textbooks. Then this list of textbooks on these slides is listed on ascending order of mathematical difficulty. So the first book is written by my PhD advisor. Of course, it's for engineering audience. And you don't need a very strong mathematical background to read the first textbook. And then the second textbook is written by Stephen Boyd and co-author. Right. Stephen Boyd is a professor from Stanford in electrical engineering. And of course, since Boyd is also an engineer, the target audience is also engineers. You don't need a very strong mathematical background either. And then after the book by Boyd, all the rest of the book, I would say they are written by mathematicians. And then you need a stronger mathematical background in order to read that. We have books related to integer programming, linear programming, global optimization. The last book is a classic book on convex optimization. Okay, it's not necessary to buy any of those books. But if you are interested in a particular topic, you may want to go much deeper into that. I will not cover in detail any of those textbooks, but then we may refer to them as references. Okay, so let's start talking about optimization. So I assume most of the audience come from one of our engineering schools. Why do we need optimization? The main reason is that the application is quite ubiquitous. In chemical engineering, we have problems related to how do you control a chemical plant, how do you design a new chemical process such that you, for example, minimize the energy cost in a chemical process. Right? That's why we teach this in chemical engineering. And in electrical engineering, for example, in power systems operation, people are solving optimization problem every few minutes in order to minimize the cost of transmitting power from one location to another. And there are other things like scheduling problems, like when you are producing different types of products in a chemical plant, how do you schedule the production of those products, right? So this is a discrete problem we will cover in the integer programming part. Another major application of optimization is in transportation. Actually, you encounter with those people almost on a daily basis. If you order a package from Amazon, how do they ship their package from their warehouse to your place, right? This is a very difficult optimization problem. First of all, they need to assign those packages to the truck drivers, right? Then the truck driver need to decide what is the shortest path to serve. Let's say the truck driver serves 500 customers on a daily basis, right? What is the shortest path to serve 500 customers? So this is a very commonly solved problem. Even in computer science, it is a very well-known problem called traveling salesman problem. Because if you think about if you want to serve 500 customers, what are the number of combinations you could serve 500 customers? Yeah, 500 factorial, right? And then if you can try to guess how many combinations are there, right? Typically, people like to argue that those combinatorial numbers are larger than the number of atoms in the universe or whatever, right? So you need very efficient algorithm to get the shortest path. Okay, and then maybe in civil engineering, since we are in the civil building, there are also people working on optimization in civil related to traffic control. Right? How do you manage the traffic lights such that you can reduce the traffic congestion? And in healthcare, they have similar problem as transportation, where maybe transportation are talking about flight attendants. How do you schedule different flights, right? And in healthcare, you also need to optimize the schedule of doctors and nurses, for example, right? And recently, there are applications of optimization in science as well. For example, if you want to predict the structure of a protein, which was awarded a Nobel Prize in chemistry last year, right? So theoretically, that is also an optimization problem where proteins will fold into the structure that minimize their Gibbs-free energy. Right, but they are very complicated force field involved in protein folding that are very difficult to solve. Right, and actually it's still not possible to get the global optimum of their Gibbs-free energy nowadays. But then maybe if you read the news, people from DeepMind, they use deep learning techniques to predict the structure of proteins. And maybe some of you are quite interested in machine learning, since AI and machine learning is a very hot area these days. If you have taken a machine learning class, you probably are aware that literally all the machine learning models are solved by optimization algorithm, right? Things like training a neural network, you use stochastic gradient descent to minimize the loss function. Okay. So hopefully that will convince you, there are quite some applications in optimization. So I would like to start with three different, very simple motivating applications just to motivate 3 different types of optimization problems. You don't need to take any optimization class. You can just follow your intuition to formulate these optimization models. Perhaps for some of those you have heard about it. Okay. So this lecture should be pretty straightforward. We want to motivate a very complicated optimization model using some simple applications. So the first example is what is called an unconstrained problem. Here we have a linear regression problem with only 3 variables, x1, x2, and x3. Okay. So this problem is, if you are into machine learning, you can call linear regression a machine learning model as well, if you wish, right? So basically, the problem you are solving is given some x variables, x1, x2, and x3, you want to predict this response function y, right? And how do you predict that? You fit a linear model where y is a linear function of x1, x2, and x3. So how do you find those beta values such that from this model, you can get an accurate prediction of the y variables? Okay. So last semester, I was teaching an undergrad class in statistics. We essentially talk about this type of problem to the undergrad as well. So maybe just to refresh our memory, anyone remember how do you formulate this problem? How do you find the optimal beta? Yeah. Can you tell me a little bit more details? How do you, which function should you minimize?
We are supposed to minimize the error.
Yeah, exactly right. You try to minimize the error given by this model compared with y. So here, the problem you are solving what is called the least square problem, right? You have 5 different observations, right? We want to find a beta such that, on average, the prediction from the linear model match the response from y. Okay, so here I is from 1 to n. You are calculating the squared distance between yi and this linear model, right? Exactly as you said, you have the least square error terms here. And you want to find the beta that minimize this error, right? So this is known as the multiple linear regression problem, and the parameters are determined by least square estimation. Okay. So the other question to ask is, perhaps you still remember that in your calculus class, right? Now I'm minimizing this least square loss, right? And then beta are the variables I'm trying to change. So how do you get the beta that minimize this loss? How do you calculate the beta? Yeah.
You take the derivative with respect to each variable and put to z.
Yeah, exactly right. So you take the derivative of this loss function with respect to each beta 0, all the way to beta 3, and set the derivative to 0, right? Okay. So the other follow-up question I have is, why is this the minimum? Because let's say, if you have a function like this, right? So this point is where the derivative is 0, all right? Of course, it is a minimum for this particular curve. But then you may have another curve where there are two points where the derivative is 0, but only one of these points give you the minimum. Why for this function, you take the derivative, set it to 0, it gives you the minimum.
Because it is convex.
Yeah, exactly, right. So because this function is convex, or We will cover that in the second lecture. The reason is this function is for convex function. If the local minimum is any local minimum is a global minimum, and a very easy fact to check is you take the Hessian of this function. The Hessian is positive semi-definite. Okay, so we'll cover those in the next lecture also. Okay, so for now, you only need to understand how we model this problem. Okay. Now the second problem is what we call a linear programming problem. Let's first talk about this problem in natural language. Then I will ask you to think a little bit about how do you formulate this as a mathematical model. Okay. So here the application is the following. A dietitian is planning a meal that meets the daily nutritional requirements for calories, protein, and vitamin at a minimum cost. So there are different food items we have, like apple, bread, milk, and egg, right? And we have the cost per atom for each of these food items. And for each food item, you know their calorie, protein, and vitamin value. For example, let's say, of course, as you can imagine, bread provides more calorie than apple, for example, right? And then maybe milk and apple provides more vitamin and so forth. Supposedly, you are, let's say, a poor man or a poor woman trying to find a minimum cost plan that meets your daily nutritional target, right? Supposedly, for someone to survive, you need 500 calories, 15 grams of protein, and 100% vitamin, right? You want to decide how do you buy, how many of these food items you should get in order to satisfy those calorie requirements, right? Well, you want to minimize the cost. Okay. So let's think a little bit for 1 second. How do you formulate this problem mathematically? Also, another note to add is supposedly you don't need to get integer number of items, right? Suppose you can cut an apple to any fraction. You can get 1.2 apples, right? Okay, yeah.
Well, then you could, your objective would be to minimize the cost of the sum of everything,
Mhm.
where the sum of everything has a coefficient in front that represents how many times you've bought it.
Yeah.
And then you would have constraints to say that the sum of everything times its protein count rather than its cost
Mhm.
adds up to that much protein, and the sum of all the vitamin counts
Mhm.
adds up to 100%.
Mhm.
You can add all those constraints to it, and then that would be formulation of the problem.
Yeah, exactly. So you could define some variable, let's call it maybe y1, y2, y3, y4 to represent the number of each food items you are going to buy, right? And the objective is to say you want to minimize the cost of those items you buy. So here you just one times y1 is y1 plus 0.5 times y2 plus 2y3 plus 0.3 y4, right? So that's the objective you want to minimize. And then the other thing is so-called the constraints, right? You need to satisfy the daily nutritional requirements. So for calories, apple provides 100 calories, so it's 100 y1 plus, basically you take this column here, right? So it has to be greater than equal to 500. Actually, you can also write it as equal to, since you are minimizing, you don't want to go over 500 and all the numbers can be fractional, right? So you could also write it as equal to. Yeah. Now, similarly, you can do it for protein and vitamin. I'm not going to write it down here, but it should be quite straightforward. So here, as you can see, this problem has some constraints, right? In the previous problem of linear regression, the problem is unconstrained. So here, you need to add some constraints to the problem because we specify we need to satisfy those requirements. So this is an example where the decisions you are going to take are continuous. Right? y1, y2, y3, y4 can take any greater than or equal to real numbers. Right? So here we have to specify y1 is greater than or equal to 0 because you cannot buy a negative number of those items. Right? Yeah, so this is a full mathematical formulation of this problem. Again, the objective is to minimize the cost. These three constraints specify you need to satisfy the calorie, protein, and vitamin requirements. And then all those variables have to be non-negative. Right? Okay. Any questions so far? All right. So let's talk about the third problem here. It is a different category of problems where the variables you have can only take integer values. Okay, so let me explain what it means here. So if you consider a hiker who needs to choose the most valuable items for a hike without overloading the backpack. So there are 3 items the hiker can put into the backpack. We have tent, stove, and food. Right? And total backpack capacity is 3.5 kilograms. So if you put all the 3 items, tent, stove, and food, you can do the calculation. It is greater than 3.5 kilogram, right? So you cannot put all the item in the backpack, right? So maybe before you travel, you will be solving the similar type of problem. You cannot put all the items you want to take in your luggage, right? So the objective is to maximize the value of items in the backpack. So each of these items have a specific dollar value. You want to maximize the value in the backpack. Instead of dollar values, you can also assign them other arbitrary value as well. Maybe like how important is that item for you, right? Rather than the dollar value. Okay. So the difference compared with the previous problem is that you cannot put a fraction number of tent in your backpack. Right? You either not put the tent or put the tent into the backpack. Right? So that is an example where the decision variables takes binary values. They can be either 0 or 1. Right? They cannot be any real numbers. Right? So this type of problem is what we call integer programs. And knapsack is one of the computational, actually very hard problem, but very, very easy to formulate type of problem. Okay. So let's just take a look at this formulation. It should be very simple to think about. So let's define some binary decision variables, x1 for tent, x2 for stove, and x3 for food. Right? So if x1 equals to 1, the item is chosen, and 0 otherwise. Right? So binary variables can only take discrete values. And then the formulation is the following. You want to maximize the dollar value of the items you put into your knapsack, right? And subject to the constraint, they cannot be exceeding the capacity of your knapsack, right? So those are one very simple constraint and one linear objective. Here, all these variables can only take 0, 1 values here, right? Okay. So that's a difference from the previous problem here, right? Well, although this problem is very simple, computationally solving this problem is what we call NP hard to solve. The reason is, here we are talking about 3 items, right? As you can imagine, as this number of items grow, right? There are different combinations you can put the items into the knapsack. Where does this type of application arise? Well, one example is in cloud computing. If you are running a server, there are different people submitting jobs to this server, right? You want to pack as many jobs as possible on this server, right? And this problem can grow, the number of combinations can grow very fast, right? Okay, so now to summarize, we've talked about 3 problems belonging 3 different classes of optimization problem. The first problem is linear least square, where you try to minimize the least square loss. And that problem is unconstrained. You can pick any arbitrary coefficients, right? The coefficients doesn't have to be constrained as long as they make physical sense. Then the second problem is this diet problem, where we have continuous decisions. You can eat, let's say, a fraction number of apples or a fraction number glass of milk. And all the constraints are linear as well. In the third problem, the difference is the decisions are 0, 1, right? It can only take 0 or 1 values, okay? So here's the 3 motivating examples we talk about so far. And you don't need to worry about how to solve this problem. Of course, for this small problem, you can even solve it by hand. But then throughout this semester, we will cover the algorithm to solve this problem to a massive scale. Okay. Any questions so far? Okay. Yeah. So after these 3 applications, let's define a general optimization problem, what is called mixed integer nonlinear programming problem. So this type of problem is the hardest class of optimization problem we will cover throughout this semester. And this later on, I will show you that this mixed integer nonlinear programming can be simplified to a much simpler optimization problem if certain assumptions hold. Okay. So what are in this so-called mixed integer nonlinear programming? First of all, we have some continuous variables and some binary variables. Okay, remember in the first 2 problems, we have continuous variables, which can take any real values. So here we assume the continuous variables are of dimension n superscript x without any loss of generality. And then we also have some binary variables with dimension n superscript y. Right? So the decision variables can be both continuous and binary. And theta represent what we call parameters of this problem. So what does parameters mean in optimization? That means the data you already know in this optimization problem. For example, if you look at this knapsack problem, all the data I gave you are so-called parameters, the input parameters to this problem. Okay. And the variables are the decisions you are going to decide using this optimization problem. Of course, the x and y have to satisfy certain constraints. Here, without loss of generality, we use this function g of x, y, parameterized by theta to denote the inequality constraints, or less than equal to here, right? So assume we have 1 all the way to m superscript less than equal to number of g of x, right? So each one of those constraints is denoted by g sub I. Okay, and the h denotes all the equality constraints. Right? So we will use 1 all the way to m superscript equality to denote the equality constraints. And f is the objective function. Okay. In the first example, f is a quadratic function. We are taking the least square problem. And in the last 2 examples, f are linear functions. Right? The knapsack cost and the diet cost are all linear functions of the decision variables. Okay. So here we define them without loss of generality, where f, g, and h are general nonlinear functions. And in the next few lectures, we will talk about, usually we assume all those functions are C1 functions, meaning that all of these functions are differentiable and their derivatives are continuous. Okay, because at least you need a first order derivative to solve some of these problems. And if the first order derivative are discontinuous, or the first order derivative that does not even exist, that's called a non-smooth optimization problem, which is not within the topic of this class. Right? There is an entire research area what is called a non-smooth optimization. Okay, but here I just want to give you sort of the heads up. This will be the most complicated problem we aim to solve. We will cover algorithms to solve this type of problem throughout this semester. Okay, but then gradually we will build it up. Okay. Yeah. So let's also define some jargons for optimization. First of all, what is a feasible solution, right? So, or does even a feasible solution exist for this problem, right? Okay, as you can see in this MINLP problem, we have multiple constraints, right? For some of these problems, maybe there doesn't even exist a solution that satisfies all these constraints, right? You can give some very simple example. I gave you 2 linear equations. It can be infeasible, right? I tell you x equals to 0, x equals to 2 as well, right? So these 2 equations gives you an infeasible linear system, right? And of course, if you have a very complicated equations, there could be the case that no solution exists. So that is called one is infeasible if there exists no feasible solution x and y. And if x and y satisfy all the constraints listed in this equation, that means x and y is called a feasible solution to the MNLP. Okay. And then if it is feasible and x and y minimize equation 1, then we can denote them as x star, y star. They are called the optimal solution to equation 1. Okay. And then the corresponding optimal objective value is what we call an optimal value to the optimization model. Okay. And the other jargon is one is called unbounded if the optimal value is minus infinity. Okay. Can someone give me a very trivial unbounded optimization model with, let's say, with one variable?
Yes.
Yeah, so you could like minimize x, right? X is unconstrained. That is an unbounded optimization model. Okay, yeah. And there are other cases. Actually, in many practical problems, the problem could be unbounded, right? Okay. So next, we will sort of give you a roadmap on what we will cover in this semester. Okay. As I said, the most complicated problem we will cover is mixed integer nonlinear program. But if you make some simplification to mixed integer nonlinear program, there are other subset of classes of problem which require a special treatment than a general mixed integer nonlinear program. Of course, if all these f, g, and h are nonlinear functions, then we have an MNLP. But if f, g, and h are all linear functions, then the problem is reduced to what we call a mixed integer linear program. This is perhaps the most commonly seen problem in the literature, actually also in practice. Most applications you find in the real world are mixed integer linear programs. Okay. And then if some of the f, g, and h are nonlinear, but they are n superscript y equals to 0, that means the dimension of the binary variables are 0, right? You only have continuous variables, then we are talking about a nonlinear program for NLP, okay? And then if f, g, and h are all quadratic functions, right? Quadratic functions means you have x transpose qx. Q is an n by n matrix. X is an n-dimensional vector. Okay. So you should write it as x transpose qx plus b transpose x less than or equal to, let's say, d. Right. That is a generic quadratic function. And then if f, g, and h are linear and ny equals to 0, we don't have any binary variables, then the problem is reduced what is called a linear program. Okay. Perhaps one of the first applications of operations research or optimization is originated from linear program, where actually in World War II they were thinking about shipping different munitions to the battlefield, right? And then they want to minimize the transportation time or the cost, and by solving a linear programs. And when should you use which problem? That really depends on the nature of the problem, right? For some of the problem, you cannot really simplify them to a linear program, right? Ideally, you want to solve a simple problem, but some of the applications are nonlinear in nature. Actually, chemical engineers were quite active in developing algorithms for nonlinear problems. It's just because many of the equations in chemical engineering are nonlinear. You can think about your thermal or kinetic equations. They are usually quite nasty. Okay. So before we talk about the algorithm to solve these problems, we want you to get your hands dirty on what if you stop caring about the algorithm for 1 second. Let's just say if we can use the software to solve an optimization problem. As long as you can build a model, you can use some of the existing software to solve these type of problems. So the software we will be talking about is called PyOmo. It's an optimization algebraic modeling language in Python. So I assume most people use the Python programming language nowadays. That's why we decide to go with a framework in Python. But if you are more comfortable with other programming language, let's say MATLAB or Julia, they are all commonly used. You are welcome to use other programming language as well, especially if your research group uses a different programming language. Yeah, you can also. There are also different frameworks to model optimization problems. Okay, but then I should caution that the course project we gave you will be in this PyOmo modeling language, right? But nowadays it's very straightforward to translate models from one language to another using those generative AI tools, so it doesn't matter that much. Okay. So I will briefly talk about PyOmo today, and then on Thursday, one of my students actually will give you a few more tutorials on PyOmo. Okay. So in PyOmo, there are different objects you can define. Sets are a collection of indices you can use to index variables and constraints. And then you already know parameters, variables, constraints, and objective. We've already talked about that, right? What they are. But then the question is, how do you really define them in PyOmo, right? I will show you a tutorial later, but let me first go through the high-level concept of how PyOmo works, right? So first of all, I want to talk about a concept called optimization solvers. Right. So what is an optimization solver? Right. Now, as I told you, Pyomo is a way where you can define an optimization model. Right. But then a solver will tell you how to solve this optimization model to optimality. Supposedly you already write an optimization model in Python or using the Pyomo framework. Then you are wondering what is the optimal solution to this model, right? Pyomo itself will not tell you what the optimal solution is. It's just a way to write down the problem using Python. But then Pyomo can be connected to several different optimization solvers. These solvers will tell you what is the optimal solution. And none of these solvers are written in Python. They are usually written in those lower level language like Fortran or C or C++. But then the job of Pyomo is to help you connect with those optimization solvers so that you don't need to talk to them in C or C++. Pyomo already does the job for you. Okay, so there are different optimization solvers. We will talk about them in detail throughout this semester. You don't need to understand how these solvers work. Hopefully by the end of this semester, you will have a rough idea of how these solvers work, what's the algorithm behind those solvers, okay? So we will talk about open source solver. That means these solvers are free. You can even get the source code of those solvers. One of them is actually developed by a chemical engineer. This IPOpt is still one of the best solvers in nonlinear optimization. And there are also well-known commercial solvers like Cplex, Groovy, and Baron. We will talk about them in detail. And then if you are curious about what are the list of solvers that can solve optimization problem, there is a link below. Let me show you real quick. So there is a link you can find where it has a list of literally most of the optimization solvers nowadays. And then the last column here, it will tell you what type of problem this particular solver can solve. For example, alpine.jl can solve mixed integer nonlinear program. That's the sort of the most general problem we talk about, right? And then there are other solvers who can only solve a subset of the problem. For example, the CDD can only solve linear programming problem, okay? And then there are solvers specialized in conic program, like second order conic program and semi-definite programs. You don't know what that means, but I will tell you when we talk about conic programming, okay? So just to keep this as one of your reference as we go through the class in this semester. Okay, okay, so this is a high-level framework of how Pyomo works. You don't need to know that in detail, but it will be nice to have a high-level picture, okay? So first of all, you need to have, of course, your data, right? With the data and sort of a business problem, you can formulate a mathematical model. Until this point is what we have already covered, right? I give you a knapsack problem, give you some data, you can formulate a knapsack model, right? But then the question is, how do you translate this model into Pyomo syntax, which I will show you some examples later. So you can translate this into a Pyomo syntax. And then, of course, if you are writing problems in Python, you can write the data in terms of lists or dictionaries, right? If you are not so familiar with Python, you can just Google what is a list, what is a dictionary. Basically, a list is like a vector to store data. A dictionary is you have a key that can map to a given data value. I will show you an example of a dictionary later. It is quite self-explanatory. Okay, so after you build a Pyomo model, then it interface with these optimization solvers we talk about, right? Again, Pyomo itself cannot give you the optimal solution. So it interfaces with those solvers, and then after those solvers solve the model and get the optimal solution, Pyomo will retrieve the optimal solution from those solvers and will return you the optimal solution. Then you can tell the user what is the optimal solution. Okay, that's roughly how it works. And there are tutorials on Pyomo. You could read those tutorials as well. Again, on Thursday we will give you a more detailed tutorial on Pyomo. Okay. Yeah. So now let me go to some notebooks to show you a couple examples we covered in class and how to write those problems in Pyomo. Okay. Maybe let me pause here to see if there are any questions. Okay. Yeah. So again, all these materials are available on the course website. So for the first lecture, if you click this Pyomo tutorial, first of all, you need to install Pyomo on your laptop, right? I would ask you to first try to install Pyomo and an optimization solver following this tutorial before Thursday, right? And then on Thursday, if you have problems installing this the software, one of my students will be here to answer those questions. Okay.
Is that like as simple as pip install Pyomo?
Yeah, so Pyomo itself is like a simple pip install. But the difficulty here is that you need to connect Pyomo with different optimization solvers, right? So you need to install an optimization solver separately. Pyomo itself doesn't come with optimization solver itself. Okay, yeah.
So I looked at those. A lot of those look like you have to like pay to get them. Can we get them for free through like Purdue?
Yeah. So that's a very good point. Most of those, let's say, especially the good optimization solvers, are not free for people in industry. But then if you have a Purdue email, you can get most of the solvers for free. So all the solvers we will be using this semester, you can get it for free using your Purdue email.
Okay.
Yeah.
Is there a list of which ones specifically you want us to have?
Yeah, exactly. So let's talk about that briefly. So this is installing Pyomo. For the moment, install these two solver. One is called IPOpt. Remember, IPOpt is the open source solver for solving nonlinear programming problem. A conda install would do the job. Okay, and then for Groovy, it is not a free solver. Actually, if you work in industry, maybe you need to pay tens of $1,000s per year in order to get access. But then they make it free for all academics. So we have a detailed step you can follow to install the Groovy optimizer. Make sure to use your Purdue email. Okay, yeah. And again, if you have problems following this instruction, one of my students will be here on Thursday to help you. Let's make sure everyone can have those example up and running by the end of this week. Okay.
Just one more thing.
Yeah.
Do you care like how we have our Python code? Like, do you care if we use VS Code, Jupyter? Does it matter?
Doesn't matter as long as yeah.
Whatever you want?
Yeah, whatever you want. Yeah, yeah. This is just I'm more comfortable with VS Code. Therefore, we give you a very brief tutorial on VS Code, right?
Gotcha.
Okay, so this is an installation guide. Hopefully, it is easy to follow. And then let me show you a couple examples of how do you formulate a problem using Pyomo. Okay, so this is a diet problem we talk about in class, right? Just to recall, you need to decide the number of apples, bread, milk, and egg you need to buy in order to satisfy those rich nutritional requirements. Right? That's a very simple linear programming problem. Okay, so I don't have a pointer here. Yeah, I can maybe read the line numbers. So first of all, for any Pyomo model, you need to import the Pyomo environment. you could have the first line at any time when you start writing a model. And then PyOMO has two different types of model. One is called a concrete model. The other is called an abstract model. I would recommend just go with a concrete model. Don't worry about the abstract model. Okay. As we said, PyOMO has different objects you can define. The first is called sets. So the sets are like the indices you are going to use to index the parameters and the variables. Here we have a set of foods, right, which are apple, bread, milk, and egg. So this is a list you use to define the sets. And then we also have a set of nutrients. Right? Here they are calories, protein, and vitamins. I just define them using Python strings here. Right? Okay, the next is you are going to import the data. If you are more comfortable with other data frames like JSON on pandas, you can save them somewhere. Here we just hard-coded as Python dictionaries. Okay, so you can check what a dictionary looks like. First of all, the first data we define are the cost, right? Basically, you want to define what each food item costs, right? That's one of the cost data you have. So apple is like $1, bread is 0.5, and so forth. And then for the nutrients, we are talking about a two-dimensional data, right? So we need to define the nutrient for each food item for each nutrient, right? So there are different combinations, like the calories for apple, bread, milk, and egg, and protein, and so forth. So this is like a table, the way you can define a table using a dictionary. Okay, and similarly, you have the requirements written as a dictionary. So all the data you can just write them as dictionaries if you are dealing with a small model. Okay, and this is a model we had in class, right? The objective is to minimize the total cost. The constraints are to satisfy each of the nutrient requirements. So how do you implement this model? After we defined the data using dictionaries, you could define parameters in PyOMO, right? So for each of these parameters, you need to index them by the sets you already defined, right? So all the variables and the parameters are indexed by sets. Okay, so for example, the content are indexed by foods and nutrients. It's the same index you used for defining the nutrient data here, right? It has two indexes, the apple and calories. Okay, then you can define your decision variables x here. So the keyword in PyOMO is var var here. And similarly, you need to index the variables by model.foods here in this case. And here in this case, remember all these variables are non-negative reals. There are different keywords in PyOMO where you can define the domain of variables. In the next example, you can find the domain will equal to binary here. Okay, here because x is a non-negative or continuous variable, then the domain equals to non-negative reals here. Okay. As for the constraints, it is slightly more complicated since we are in Python. You need to define the constraints as a function. Okay, so to define any function in Python, as you remember, you need this def keyword here. Let's call this constraint nutrient rule. Okay, and the nutrient rule is parameterized by the model and nutrient because you want to define the constraint on top of the model. That's why you always write a model here. And here you can read this constraint as just a sum over all the food items you got should satisfy each of the nutrient requirements. Okay. And then you will add this function to the model by defining model dot nutrients constraints equals to, again, capital constraint is another keyword in PyOmo. That is a way you can define constraint. And this constraint is defined on top of different nutrients. That's why in this constraint keyword, you have a model dot nutrients here. Okay, so let's go back to the constraint to take a look at it. So as you can see, we have 3 constraints defined for each nutrients, right? The calorie, protein, and vitamin. So therefore, in order to define this constraint generally, you need to index the constraint by nutrients because you have 3 different nutrients here, right? That's why, as you can see, in defining the constraint, it is defined on top of model.nutrient. So with this keyword, what PyOmo does is it will iterate over all the 3 nutrients you have defined, right? So remember, model.nutrients is defined as a set here. As you can see in the, when we define the set, model.nutrients involves 3 different nutrient items, right? And the constraint is defined on top of this set nutrients, okay? Okay, and then later on you want to define the objective, which is minimize the summation of the cost. That should be easy to understand. Okay, so up until this point, we've defined all the variables, constraints, and the objective function. Right? Now you are ready to solve the model. If you already installed Groovy, and then you tell PyOmo where Groovy is installed by following our instructions, you can use the solver Groovy to solve this model. Okay, so you just do solver factory. So solver factory is an object in PyOmo where you can use the solver factory to connect to different solvers. For example, if you have IPOpt installed, you could do solver factory IPOpt and use IPOpt to solve this model. Okay. And then, as in most of the PyOmo Python code, you could print out the solution. Right? It should be very easy to understand if you know. If you know Python before. Okay. Yeah. So to start with, I would suggest you try a few small examples we've covered in class. We will also give you a few easy homework problems to solve such that you are familiar with the syntax in PyOmo, right? So at this moment, try to study the example and write the models yourself, right? Later on, actually writing a model is very easy. If you plug in the problem description into ChatGPT, it will generate the PyOmo model for you. There are actually people working on this research area of how do you translate from natural language into code. Okay. Yeah. So then the second example is a binary knapsack problem. I won't go to the details of it. It actually follow exactly the same procedure. You define the model, the sets, define the data using dictionaries. Then, of course, here, the model has 3 binary variables, x1, x2, and x3. Okay, so pay a closer attention to the decision variables here, where when you define the decision variables, the domain becomes a binary instead of non-negative reals, right? So that's a way you define binary variables in PyOmo, right? Otherwise, if you define it as a continuous variable between 0 and 1, it will give you some fractional values. You could try to play with it and say if you define x as non-negative reals and resolve this problem and see what happens. Right? It will probably give you some fractional solution. So I won't go to the details of the objective and weight. You could read line by line, see what it is doing. So as you can see, after you solve this problem, then the tent equal to 1, stove equal to 1, food equals to 0, right? It all satisfies the binary constraints. Okay, so those are the brief tutorials I want to go through here. Are there any questions? Okay, so you could try to play with this Jupyter notebook as well as trying to install Pyomo yourself on your laptop, and also the two solvers, right? If you have questions on Thursday, one of my students will be here to answer those questions, and he will first go through a few additional Pyomo tutorials on more complicated problems, just to give you some intuition on how to formulate optimization models. Okay, and next.